to see how I can say it. So he will be talking about medium evolution of a QQ par pair in the large NC limit. But before I let you start, I think you have 30 minutes, 25 minutes for your talk and 5 minutes for questions. So let's welcome our first speaker.
Okay. Thank you very much for the opportunity in this nice workshop. So my motivation is to study quark-anion suppression, and that is the reason we study all this. So first I'm going to introduce a little bit the problem of quark-anion suppression, and then in the second part I will discuss why I think that we can learn a lot of things from the static limit and how an effective field theory that is called potential non-relativistic QCD can be useful to connect the static limit with a real quark-anion. And then I will discuss in the third part how to the evolution of a static pair in a thermal medium. Okay, so heavy quark-anion is a bounded state of heavy quarks whose mass is larger than QCD. So this implies that the heavy quarks can only be created in a hard process at the beginning of the collision. And however, the system of the medium modifies the probability that we get a bound state at the end. Therefore, measuring the nuclear modification factor, we can extract information about it. Okay. So there are several phenomena that may lead to dissociation. One is color screening, which was introduced in the first paper of quark-anion suppression. And the idea is very simple. If you are in a regime in which you can study quark-anion with an effective potential, for example, that you will have in a perturbative limit a Coulomb potential, now at final temperature, you have to substitute it by a Yukawa potential that has a Debye mass. So if the Debye radius is bigger than the size of the quark-anion state, then the heavy quarks cannot form a bound state, and therefore this leads to dissociation. However, this is not the only process. The medium contains many particles, and they can hit quark-anion, which is normally a stable state of heavy quark antiquark, and then you can induce a transition to an octet state, which has quark-anion will dissociate because the interaction is not attractive anymore. Then this means that you can have a dissociation without screening, without the mechanism previously proposed. And this is the mechanism that is behind the imaginary part of the potential. However, you can also have the opposite process. You can have two heavy quarks that meet inside of the medium that maybe they were initially uncorrelated, and they meet to form a new quark-anion state. Okay, so we need a formalism in which we can include all three mechanisms consistently. And we know that if we are considering screening, the question we are asking is whether a bound state solution exists or not. And this is a question for which we need quantum mechanics. If you're studying the decay weight and recombination, in some cases you can use a Boltzmann equation or a semi-classical approximation. However, this is not always the case, and it is not the case when these effects are not a perturbation. Therefore, we need a formalist to include the three mechanisms that considers quantum mechanics. And one of these formalists could be that has been proposed in the last years is the use of the formalism of open quantum systems. So here you consider that your universe is made of the heavy quarks that we call the system, and the rest of the particles, that is the medium of like quarks and gluons, which is the environment. And then the density matrix of this universe will have a unitary evolution. However, it is interesting and simpler to, instead of studying the evolution of all the universe, to study the evolution of just the heavy particles. So for this, you define the reduced density matrix which you obtain when iterating out over the environment degrees of freedom. Then now the evolution of this reduced density matrix is not unitary anymore. And in fact, the equation that draws the evolution of this reduced density matrix is generically called a master equation. And what you need is to, well, this master equation recovers in a specific limit the Schrödinger of the Boltzmann equation, and you need to derive it from QCD. So at the moment, it has been using perturbation theory, or using the effective field theory potential non-relativistic QCD, which I will discuss a little bit more in the next section, in the regime in which the medium sees quark-onion as a small colored dipole. Okay, so well, in this master equation, I'm going to skip this slide, but just to mention that this master equation when in the Markovian limit takes the Lindblad form, and well, this is it is challenging to solve this equation in order to get phenomenological results. And recently, there's some computational techniques have been used to reduce this cost. And Mike Strickland will talk a little bit more about this tomorrow and the phenomenological results that you can get from this approach. And you can also connect this open quantum system framework with the Boltzmann equation and other semi-classical approximation in the specific limits. So very roughly, what you want is to connect the master equation to phenomenology, and this can be more or less challenging. But what I'm going to focus now is the first state. Okay, so before connecting the master equation with phenomenology, you need to derive it from QCD. And what we know until now is how to do it using perturbation theory, using the Harter-Marlock theory, and also potential non-relativistic QCD in this limit. So the question is, okay, can we say something about the regime in which the medium does not see quark-onion as a small colored dipole? And it would be great. So in principle, we expect to get some expectation values or some operators or Wilson loop. And it would be great that we could get this information also in this regime. And if so, what could we learn by using the largest limit? Okay, so these are very complicated questions, but I will try to convince you that we can get a lot of insights from studying the static limit. Okay, which is what I'm going to discuss now. Okay, so in summary, I'm going to review potential non-relativistic QCD at t equals 0, and review why the singlet potential, which is a Wilson coefficient of this effective field theory, coincides exactly with the static potential and understand the physics behind it. I will also try to explain some of the difficulties that you may find when you extrapolating this argument at t equals 0 to finite t. Okay. Well, in theories are useful because you have widely separated energy scales in many problems. In the case of quark-onion, you have the mass of the heavy quark, which is larger than lambda QCD, the temperature of the medium, this is smaller than the mass, and quark-onion being a non-relativistic system, it also has lower energy scales, like the inverse of the radius, that goes like mv, v being a small velocity, and the binding energy. Effective field theories are useful in these situations because when you have widely separated energy scales, you can have a breaking of naive perturbation theory. And even if you're not doing a perturbation theory, if you're in the lattice, you can find that you need very large lattices to fit all the relevant energy scales. Okay, so in the case of when studying quark-onion or heavy quark diffusion, one natural step is to integrate out the scale of the mass. And you can do this always perturbatively, and we assuming ignoring the medium because the mass is much bigger than lambda QCD and the temperature. So what I'm going to discuss next, it is useful to classify the gluons in the following way. We have hard gluons with energy and momentum of order m, soft gluons with energy momentum of order mv, and ultrasoft gluon with energy momentum of order mv squared. And then we have potential gluon with energy of order mv squared and momentum of order mv. So if you start from QCD and you integrate out the interaction with the hard gluons, you arrive to non-relativistic QCD, which is useful in many contexts, and in which you go from a B-spinor field for the heavy quark and the antiquark to a spinorial field for the quark and another anti-spinorial field for the antiquark, and you see that the Lagrangian has many reminiscences from atomic physics. If you also integrate out a soft and potential glue, and then you are at triple zero, then you arrive to potential non-relativistic QCD, in which the degrees of freedom are singlets and octets. And if you are in this regime, so if the medium cis-quarkonion has a small color dipole, you can do the matching between non-relativistic QCD and potential non-relativistic QCD at t equals 0. And in fact, this is what has been used in the past to get the master equation. Okay, so well, this effective field theory has several Wilson coefficients that in principle are difficult to compute because the matching between non-relativistic QCD and potential non-relativistic QCD is not always perturbative, but you can follow this following strategy. So both non-relativistic QCD and potential non-relativistic QCD are valid for any value of the mass. And in particular, they are valid when the mass goes to infinity. And moreover, we know how is the scaling of each Wilson coefficient with the inverse of the mass. This means that we can do the matching in the static limit and then use the results for any value of the mass as long as quarkonion is non-relativistic. Then we take non-relativistic QCD in the static limit and potential non-relativistic QCD when this singular potential here is a Wilson coefficient. Then you do the following. You create in non-relativistic QCD an interpolating field that transforms like a singlet and at leading order up to term suppressed by R is proportional to the singlet in potential non-relativistic QCD. Then if you compute the propagator of this field, this is just the static Wilson loop, and this is what you get in potential non-relativistic QCD. So what this is telling you is that this Wilson coefficient that you can use in any computation in potential non-relativistic QCD is exactly the static potential. The physical picture that you can take in a more or less hand-waving way is the following. So the evolution of the density of the wave function takes a time of this order of magnitude, which is quite large. And this is compatible with the time it will take a quark moving at the speed v to go through a distance of order of the point state. What this means is that from the point of view of the gluons that are relevant for matching non-relativistic QCD to potential non-relativistic QCD, the quarks are effectively static because they move very slowly. Okay, so things get complicated when you, as you know, when you are at that finite temperature, because there is a doubling of degrees of freedom. You have to introduce this Schwinger-Keldy's contour. And okay, so if you are in the, as I said before, if you are in this temperature regime, you can ignore all this because you can do the matching at equals 0 and then get the evolution of the density matrix. But if you're in this regime, you cannot ignore this anymore. Okay, so what happens is that in the vacuum, so in the non-relativistic QCD part, because you will have that an exponential in the part integral of the action in the upper branch of the Schwinger-Keldysh contour minus the action in the lower branch. However, in potential non-relativistic QCD, we know that this is not going to be the structure because we have an imaginary arc. So it means that we will have terms that will mix the two branches of the Schwinger-Keldysh contour. And to my knowledge, it is not known yet how to do this, in how to construct an effective field theory in this way that has this phenomenon. Okay, so nevertheless, the physical argument that I was saying before, in my opinion, are still valid. So, well, just take it as a justification that at t equals 0, all you need to know to get the valid form of potential non-relativistic QCD is the static limit, or in other words, is the only thing that you need to compute non-perturbatively. And then this motivates studying the static quark at finite temperature in order to someday get information that is useful for real quark. And with this, I move to the study of the static limit. So I'm going to use this notation in which I have this Vertex notation, which arrows go from vector to anti-vectors. A straight line represents a Wilson line in the fundamental representation, and a dashed line represents a Kronecker delta integral. And then a Gelman matrix will look like this, and the singlet and octet field will be something like this. And then what we need to use is that in the evolution of a static quark, as you saw in the non-relativistic QCD, the static limit is just a time-like Wilson line. And we also use the Fierce identity. And then using this, we can get the backwards evolution of the singlet and the octet. And then you can ask the following question. So given that, so if I have a singlet at time t0, what is the probability that I find a singlet at time t? And then what you get is that this probability is the expectation value or the trace over the environment of the expectation value of a time order Wilson loop multiplied by an empty time order Wilson loop. You can make the same for a singlet going to an octet, for an octet going to a singlet, and for an octet going. Okay, so this is a very formal expression, difficult expectation values that mixes the two branches of the Schwinger-Keldysh contour. However, we can get some insights from making the Larsen-C limit. For example, in the case of the singlet to singlet transitions, you see that gluon, so diagrams that mix these two Wilson loops are suppressed. What this is telling us is that actually this expectation value of this multiplication of Wilson loops is actually approximately equal to the square of the expectation value of one single Wilson loop. And this is suggesting that the survival probability of a singlet can be encoded in an effective Hamiltonian. And moreover, this Wilson loop that you have here is exactly what is computed in the lattice nowadays to get the static potential, also at finite temperature. Regarding the singlet to octet transition, what you can say is that the probability to get an octet is just the probability to get anything minus the probability to get a singlet. And both these terms scales in a similar way. And regarding the octet to singlet transition, you can say something similar as to a singlet to octet. But now you see that both terms are suppressed. So it will indicate that the octet transition to a singlet is suppressed in the partition. And regarding the octet to octet transition, you see that it's dominated by this term. And it also happens that terms that connect the heavy quark with the anti-quark are suppressed. So what this is indicating is that the octet evolves similarly to an uncorrelated pair of heavy particles.
So you have 5 minutes.
Okay. Okay, then with this, you can establish in a formal way the evolution equation of a static pair in which these functions are written in terms of the Wilson loops I shown before. So I'm not going to discuss the details now, but when done this case is the scaling with the Larsen C. So when the density of singlet and octet are similar, what we have is that the singlet will evolve in an evolution that could be encoded in an effective Hamiltonian and is not very affected by the density of the octet, while the octet evolves like a pair of uncorrelated particles plus a source coming from the decay of the singlet. However, this is not stable. This will lead to a situation in which you have very few singlets. And when you are in this situation, what happens is now you have so few singlets that it is important to take into account the decay of octets into singlet, even though it is suppressed. But for the same reason, the evolution of the octet is you can ignore the decay of singlets and they would evolve as an uncorrelated pair of particles. Okay, so with this I arrive to the conclusion. So I try to convince you that the physics of static quarks can be relevant for the study of real quarkonia. So this evolution can be written instead of expectation values of Wilson loops that mix the two branches of the Swinger-Keldy's contour. So a question will be if there is some way to compute this kind of operators non-perturbatively. And we can also get some insight from the Larsen C limit. So I haven't discussed this in detail, but the results that we found here are in qualitative agreement with the previous derivations when you do the Larsen C limit. And they suggest that the evolution of the singlet can be encoded in an effective Hamiltonian. And this will justify solving the Schrodinger equation with imaginary potential. And regarding the octet, okay, this study was done for only one pair of particles, but if the conclusion that we get will be maintained for the case in which you have many particles, this will be a support for the molecular chaos hypothesis that is often used when solving the Boltzmann equation for the study in quarkonia. And that's all. Thank you very much.
Thanks for this nice talk. Now we have almost 6 minutes for questions. So anyone with questions? We have 6 minutes, so I think we need 6 questions to fill them in. So I will ask one until, okay, so go ahead, Mike.
So Miguel, is it clear? So it looks like the H effective evolution will dominate in the large NC limit. And that means that perhaps we can use these more phenomenological potentials like Ángel and I used and just have some imaginary part to it. Are there limitations on what you can do on the phenomenology side for getting H effective evolution? Should we stick to PR and QCD in that case? And only use the effective potentials that come out for singlet and octet in that case, for example. The other question I have is that in the imaginary potential case, usually people only model the singlet part. So this throws out all of the octet evolution. Is it okay in that case to use the leading order PRN or QCD potentials as source of the imaginary part?
Yes, no, I think so. I mean, regarding, well, I don't know if I'm going to answer what you asked, but yes, I mean, in what we see is that, okay, the expectation value of T squares of the, yes, of the square of these two time order Wilson loops is actually the square of the static Wilson loop that you compute in the lattice. And this is exactly, I mean, if you would do a non-perturbative matching with non-relativistic QCD and potential non-relativistic QCD, this is precisely, so computing this guy here is precisely how you will get the singlet potential with its imaginary part in potential non-relativistic QCD. So in that sense, it's equivalent.
So this would advocate then for using the lattice measured imaginary part and real parts of the potential as input here for the H effective evolution.
Exactly. I mean, yes. I mean, this in potential non-relativistic QCD, you can do the matching perturbatively, but you can also do it non-perturbatively. And then the way that you do, I mean, the two are consistent. I mean, if you could go and get it from the lattice. So
okay, thanks, Mike. Thanks, Mike, for the question. Any other questions? We still have 4 minutes for questions, if anyone have a question. So I have one question. If you can go to your conclusion, you said, you advertise for using the, the importance of the static quarks. Do you know that, this physics is considered in some models where people use the, the static quarks? You said, I didn't know if my question is...
See, if there have been computations of Quarkonian suppression, just assuming the exact static limit. If this is your question.
No, my question is about your first point. You said the physics of static quarks can be relevant and important when studying real quarkonium. Do the some models use them?
The physics of static quarks.
Yes.
I mean, yes. Arguably, I mean the computations that they have shown they use many ingredients from the static quarkonium. I mean, the ones that are based in potential non-relativistic QCD, they use a lot of physics from the static quarks in the sense that the matching is done in this way. And, okay. And many theoretical computations, and I mean, they have been first done using the static limit. I'm not aware of, phenomenological complications and consistently using the static limit all the time. So ignoring that quarks are moving. But yet I will guess that they will give qualitatively similar results.
Okay. Okay, so by this, let's thank our speaker.
Okay, thank you.
Thanks so much for this nice talk. And now it's the time for our second talk. So our next speaker, are you ready?
Hi, yeah, I'm ready.
Okay. So if you can put your slides on, please.
Yep.
Be sure that everything is okay.
Yeah, seems to be the case.
Okay, so welcome to our second speaker, Travis Dorr. He will be talking about the out of equilibrium search of the QCD critical point. And you have 30 minutes, 25 minutes for your talk and 5 minutes